In section 8.5, we'll study center of mass. Here our goals are to differentiate between center of mass and center of gravity, so we'll talk about each of those. We want to be able to solve for the center of mass using some summations and integrals. And we also want to be able to apply the concept of center of mass to things like balance and other everyday situations. The center of mass is really just an average. If we take the average position of a system's mass, a system will move and accelerate as if all of its mass were centered at this average or at this center of mass. And when we look at an object and the way that it moves, it may behave as if all of these external forces are basically acting relative to this center of mass. Now, as long as your forces are exerted at the center of mass, so maybe we have a system of two particles that are joined together. With this particle being the larger, the average of the position of mass is probably going to be closer to this larger side. So the center of mass might be located here. As long as our outside forces are exerted from here, we will see them behaving as if its acceleration is based off of that external force exerted at the center of mass, and all of the mass, some big capital M, being located at that center of mass. Basically, the center of mass allows us to use this particle simplification model that we've been using already for systems and extended bodies. If that force is applied at the center of mass, the entire system moves and accelerates as if all of its mass were a single particle at that particular point where your center of mass is. For now, we're looking at examples where forces will be applied at the center of mass, which basically means we're going to ignore rotation. What you're seeing in the figure up here is that if the force were exerted somewhere other than the center of mass, maybe on one end of the object, we would see the center of mass still moving and behaving in very predictable ways, but there would be some rotation with that. Notice that for the picture of the wrench, the light colored dot there is your center of mass. And that center of mass is behaving in a very predictable way as it moves in equal intervals across the photo that we have here. And it's moving in a nice straight line. The rotation of the wrench is sort of moving around that, but the center of mass behaves in a very predictable way. Now, since center of mass is an average position of a system's mass, we can actually find the center of mass just like an average. Basically, we look at various pieces of mass and where they're located. So an m times an x, or an m times a position. Add up all of those little positions of that mass, and then divide by the total mass of the object. This equation would find the center of mass in an x direction. So let's try this once. Let's say that we have a picture that looked kind of like what I drew on the last slide, where one object is larger than the other. So over here we have m1, and over here we have mass 2. But mass 2 is about twice the size of m1, so m2 could really be written as 2m1. Now this is a system, and we're looking for where is the center of mass along this system. We know intuitively that if the center of mass is an average of all of the mass in the system, it should be located a little closer to the larger mass's side. So it should be located closer to m2 rather than being located at a halfway point. Now if we say that m1 is located at a position of 0 along, an x-axis that we could draw in here, and m2 is located at some position d, we can use our equation to find the center of mass of this system. Remember, center of mass is just taking the position of each mass, so m1 times an x1, adding them up, m2 times an x2, and then dividing by the total mass of the system. So if we do that with this particular problem, m1 was located at a position of 0. m2, which is really twice m1, was located at a position of d. And the total mass of the system is going to be m1 plus m2, where again m2 is twice m1. Now this term, because m1 was located at 0, goes to 0. And what we are left with as we begin to simplify this problem is we have a 2m1d on top, and we have a 3m1 on bottom. The m1's cancel out, and we're basically left with the center of mass being at 2/3 d. Again, that value makes a lot of sense, because we know that it shouldn't be at the halfway point. It should be closer to the m2 side, or the larger mass. So 2/3 of the way there would make a lot of sense for that problem. This concept of center of mass can be extended to many particles in 3 dimensions. Simply apply the average position equation to each dimension separately. So in the x direction, this would look like an m1x1 plus an m2x2, on and on and on, for as many particles as you have, divided by the total mass of the system. So this finds your center of mass for the system for any number of particles, n number of particles, where the subscript I in the equation that we have here is really representing the ith particle, or whichever particle you're talking about. Maybe it's this one, maybe it's this one, any one of those particles. And capital M is representing the total mass of the system. This same equation is going to hold true for both the y and the z directions. So when we're looking for the center of mass in the x direction, we'd add up all these mx positions and divide by the total mass. In the y direction, we'd add up a whole bunch of m1y1s plus m2y2s, as many as those are, and divide by the total mass. And in the z direction, we do the exact same thing. So that overall, we could simplify the center of mass equation to just look like a summation of these m's and r positions divided by total mass. Finding the center of mass for an extended object rather than a system of particles, what we're looking at here, it's a little different, because what we're looking at here when we are using these equations is we're saying there's a bunch of particles that are located in these different positions, and we're just going to sort of add up all their positions, where they are and how much mass is there. But an object isn't necessarily a whole bunch of little dots of particles. Instead, it could be more of an extended object, like maybe a baseball bat. And so this is also made up of a whole bunch of little particles that make up this extended object, each of them with their own little bits of mass that exist there in their own positions, on an axis if we were to stick our bat on an axis. So finding this extended object is a little bit more complex. What we find is that it really is based on the same concept. We still model this object as a system containing a large number of particles or elements, and each element has its own little bit of mass and its own coordinates for where it's located. And as we let this number of elements approach infinity, so there's infinitely many of these little pieces inside of this bat, we're really summing up all of those little mx or my positions. And ultimately, we know from our calculus experience that summing up a whole bunch of stuff is really just an integral. So what we're going to do is sum up the number of elements. Again, as that number of elements approaches infinity, their size approaches 0, and we have an integral that we're working with. So in the x direction for an extended body, we would find the x center of mass as 1 over the total mass multiplied by the integral of x dm, where dm is some little infinitely small piece of mass and also the variable that we are integrating with respect to. This works for the y and the z positions, and I'll show you some of these when we get back into class. We can place limits over these integrals for where the mass is actually located. For example, if mass exists from 0 out to maybe 5 units, whatever that unit is measured in, then we can place those limits on our integral as well. And that will help us evaluate where mass is actually located. Now, if we have a homogeneous symmetric object, the center of mass is just going to lie in an object of symmetry. If you have a sphere, it will lie in the center of a sphere. If you have a cube, it will lie in the center of that cube. So as long as you're working with symmetric objects, finding the center of mass, as long as you have uniform density, will be a very easy thing to do. Center of mass is oftentimes confused with center of gravity. Center of gravity is its own concept, however, they will oftentimes coincide. What we're talking about with center of gravity is since gravity pulls on each little bit of mass in an object or system, the net effect of all these little forces is a single force, capital Mg, acting at the center of gravity. So center of gravity is really an average position of the gravitational forces that are acting on an object. Now, if the gravitational field is uniform over the system or the object, then the center of gravity is going to coincide with the center of mass. They'll be the exact same position. For most reasonably sized objects, they will be the same position. But if gravity is not uniform over the system, then the center of gravity and the center of mass can be different. And let me show you just a really extreme example of what I'm talking about here. Let's say that this is the Earth. And outside of the Earth, we have a ridiculously large space shuttle. So here's our space shuttle over here. Now, because the space shuttle is so ridiculously huge, what we'd find is that maybe the center of mass of the space shuttle, might lie somewhere in the middle of the space shuttle. So this might be center of mass there. But center of gravity depends on the gravitational pull of all the little bits of mass. So this little bit of mass over here is being pulled on by the gravity of the planet. And this little bit of mass over here is being pulled on by the gravity of the planet. Well, since we're looking at, the nose of this rocket being relatively closer to Earth, the gravitational field will be stronger here, and there'll be a larger pull from gravity on the pieces of mass that are close to the planet Earth. Because all the little bits of mass over here are much further away, the gravitational pull is going to be weaker, and the force there is going to be smaller. So center of gravity would actually be located somewhere closer to the nose of the ship when we average together all of these little bits of force that's being pulled by gravity. Now, of course, we're looking at a very extreme, kind of ridiculous example here to make this obvious what we're talking about for the difference between center of mass and center of gravity. In most cases, center of gravity is going to coincide with your center of mass, and they'll be the exact same location. In fact, finding the center of gravity is very easy to do experimentally, which means you can also find the center of mass in most of these cases very easily. And even if your object is a very irregular shape, you can find this center of mass and the center of gravity pretty easily. All you need to do is suspend the object from two different points. If you draw a plumb line, which basically means just a straight vertical line down to the ground, a plumb line from each suspension point, the intersection of those points will be your center of gravity, and therefore your center of mass as well, as long as you're in a uniform gravitational field. So when the object is hung from any point, that vertical line through that point will pass through the center of gravity. So notice in these diagrams here, we have this irregularly shaped object down here. And if we suspend it from this point, we see this plumb line that's being drawn through. And then they suspend it from a different point. So they've basically rotated the object and suspended it from another point, drew another plumb line, while the other plumb line was still drawn on there, meaning that the intersection of these points is now your center of gravity and also your center of mass. Center of gravity and center of mass do not always have to be within the object. There doesn't actually have to be mass there to coincide as a center of mass or a center of gravity. Notice with this C-shaped object, when they suspend it, they draw the plumb lines again, but the plumb lines intersect in a position that is outside of the shape. That's okay. Some objects will actually have a center of mass or center of gravity that is not in a location where any mass actually exists.